All right, so let's get going on today's meeting. So what we're going to be doing today is we are going to start our look at the normal distribution. And the normal distribution, as we're going to see, is a very important concept in statistics. And we are going to either be using the normal distribution or things that are like the normal distribution for the remainder of this course. So we are going to shift gears today and start taking a look at how our understanding of distributions and how data is spread out, where the center of that data is, and basically how it can be represented graphically, how that's going to start really paying off now when we take a look at one of the most important distributions, which is the normal distribution. So on the schedule today is going to be our intro into the normal distribution. And I mean intro into it because this is such a huge topic that it's going to take a few classes to cover all that we need for statistics. So this will be our first sort of foray into this topic here. And we're going to start off with very briefly just a reminder of the difference between discrete versus continuous variables. Then we're going to define what a density curve is, because that is a general type of curve of which the normal distribution is one of those. And then what we're going to do to try to really get a handle on what a normal distribution is and how we're going to be working with it is we're going to have a do it with me demo where you are actually going to build your own normal distribution. So we're going to model IQ scores, one of the most famous normal distribution that we know of, and you're going to see how you can actually build your own normal distribution based on the fundamentals of why normal distributions occur. And then hopefully that'll give you a peek behind the curtain so that you will have a more intimate understanding of what a normal distribution is, and thereby have a better grasp of how to use a normal distribution. So this is going to be our first official foray into the next stage of our statistical journey. So we've already started it a little bit with probability. However, this is now going to be our official beginning, and we're going to leave behind focusing on our elevator pitch, and instead we are now going to start looking at inferential statistics. Now, the skills that we developed for that elevator pitch section of our understanding, those are still very important. So you're going to see means and standard deviations and histograms all over the place as we move forward. But now we're going to switch from trying to summarize data into trying to predict data, try to infer things about data, basically going from a sample and using statistical procedures intelligently and rigorously and objectively be able to generalize from that sample to a population. So it's going to start here in full effect with our look at the normal distribution, but that is the goal from here on in, to take a small collection of data, a small sample of data, and then be able to objectively and with a rigorous procedure generalize from that data to a population, thereby being given us the power to help more than just the subjects that are in our experiments, but to help the entire population of individuals that might need our help. All right, and then today we are going to resume our ComROM. So you might remember for the last couple of meetings, our Excel program was very lonely, carrying a torch for us, but we weren't around. But today we're going to reunite. Yes, it is the ComROM Part 2, the sequel, and we are going to see how you can go into Excel and very easily and very straightforwardly create a normal distribution using a randomization function, which is just an amazing function that Excel has that will allow you to simulate many different scenarios. So once you leave this course, you can be able to use this skill to basically simulate multiple different scenarios once you know how to set it up. And that will give you a lot of power to sort of predict what could happen based on simulations that you run. All right, so all of that today. So let's start off with just a brief reminder of discrete versus continuous variables. So we encountered this in the text when we were taking a look at how to graph data and how to graphically display data. So a discrete random variable is one that often results from counting something. And what we mean by discrete is that these variables, the values that they take, they increase or they decrease discretely, hence the term discrete random variable. But that basically means that they increase or decrease in whole numbers. So a discrete random variable would be measured in terms of your score on it might be 10, or your score on it might be 11, but your score will never be 10 and a half, right? They're discrete, they have definite units to them, and they move in those whole units. Now, the other type of variable is the continuous random variable, and this one often results from measuring something. And again, straight there in the name, they're called continuous random variables because they increase or decrease continuously, and they're often expressed by decimal numbers. So you can score 10.5 on a continuous random variable. You can score 10.54 on a continuous random variable. Technically, you can score 10.5418243427 on a continuous variable because they increase or decrease continuously. So to give you a more concrete example of that, let's say that we were, looking at the population of adults. And we were interested in the different types of attachment styles. So we were interested in specifically the avoidant insecure attachment style. So this is a pattern of relating to others where a person tends to minimize closeness and emotional dependence. This is a learned response, sometimes in childhood, where expressing your needs or relying on others isn't consistently rewarded. So they cope by turning away from intimacy, not making those commitments, basically pushing people away before they get too close. So let's say that you were interested in avoidant insecure adults, and you wanted to count in this photo here, out of those adults, let's say that we knew how many of them, or we knew which ones were avoidant and insecure, we could have a discrete random variable and count how many of the adults in this picture are avoidant insecure adults. So we could say, well, let's start counting, and we have this individual here, avoidant insecure, so that's 1. And we have this individual here, that's 2. And we got 3, 4, 5, 6, 7, 8, 9, 10. I believe that's everybody. So we have 10 adults. So that is a variable because we have 10 adults. We might have had 12. We might have had 3. We didn't know how many we were going to have, so we had to count that. So we measured that. But it's a discrete variable in the sense that it's only ever going to increase or decrease in whole numbers. So we have 10 adults that are avoidant insecure in their attachment style. It can't be 10 and a half, right? We're not going to get a half adult that is avoidant insecure. So therefore, this is a continuous random variable. On the other hand, let's say that we have a theory and we say to ourselves, well, maybe one of the reasons that adults develop avoidant insecure attachment styles is because they're below average in height. Maybe that's just one of the things that contributes to developing this style. So you might say, all right, we're going to identify the avoidant insecure attachment style. That's a continuous random variable. But now we're going to measure how tall are each of these adults. So we might say, all right, well, this guy right here, how tall is he? Now that is a continuous random variable because this individual, their height is measured on a continuous scale. So in all practical terms, you might be thinking to yourself, well, really, you might be thinking to yourself, well, that's kind of a discrete scale because you're only ever measuring in inches or half inches. The point is not to get confused about that, but if you can theoretically measure it as a continuous measure, then it's a continuous random variable. So this person here might be 5'10" and a half. This person here might be 5'6". This person here might be only slightly taller at 5'6.487253, which you could if you had a measure that accurately if you had the correct tools. And again, you can measure the height of this individual here. And heights would be a continuous random variable. And that is because you can increase height by whatever small little increment that you want. So the increases and the decreases are continuous. And again, if we wanted to accurately represent these heights, we would oftentimes have to resort to decimals for that continuous random variable. So we're going to focus our look today on continuous random variables. And continuous random variables, when you graph or display the frequency of continuous random variables across the range of values that they take, what you end up with is not a histogram, but a density curve. And a density curve is a lot like a histogram, except it's for continuous random variables, and it has two properties that make them massively valuable and massively powerful to work with. So a density curve models a probability distribution of a continuous random variable. So it is a model of how a continuous random variable is distributed across all of the scores. And this model or this curve, which is basically, you can think of it as a histogram, it's always on or above the horizontal axis. So it only takes positive values. And it has, and this is the big one, it has an area of exactly 1 underneath it. So under that curve, from the curve to the x-axis, if you color in the area under the density curve, you're going to have an area of exactly 1. And what that means is that that area can be scaled to 100%. So those are the two properties that make density curves extremely, extremely useful to use. So let's take a look at one of the more kind of well-known density curves. And we're going to take a look at the density curve for the continuous random variable of height. So this is from the Our World in Data World Survey of Heights. And I'll read the caption there. It goes, the distribution of male and female heights. The distribution of adult heights based on large cohort studies across 20 countries in North America, Europe, East Asia, and Australia. And then this is all the ages between 18 or 18 as of 1998 and 2012. So let's zoom in a little bit on this. And let's make sure that we know exactly what we're talking about here. So we have two curves here. We're going to take a look at one at a time. We'll take a look at the men, and then we'll take a look at the women density curve. But importantly here on the x-axis, we have height. So going to the right, you have larger and larger heights. You have increasing height. And then going to the left, you have smaller and smaller heights. So on the x-axis here, we have height. And then it's not shown, but the implied y-axis here, that is frequency. And that would be basically how many individuals have that particular height in the population. So on the y-axis, the higher the line, the more frequent that particular height is in the world. So it's like a histogram in those two kind of respects, in the sense that we have an x-axis with the random variable on it, and then we have a y-axis with the frequency on it. It's just not displayed here because we know that certain things about this density curve, specifically that the area under it is equal to 1. All right, so let's take a closer look at these two curves here. We're going to start with the men. And the first thing to know is that this is a density curve, first because all of it is on or above the horizontal axis. So it represents frequency on that y-axis, and you can't have a frequency less than 0. Something might never happen, that's a frequency of 0, but it can't less than never happen. So you'll never have a frequency that goes below it. So the curve is always above the line. And then between the horizontal axis and the curve, you can color in that entire area. So we color in the entire area of that curve. And a density curve has an area that is equal to 1 or 100%. And that is going to be what makes these things really, really useful for us because they're scaled so that their area is equal to 1. So it makes the calculations of different parts of the curve and what areas under different parts of the curve, which is what we're going to be doing for inferential statistics, way, way easier. So if you take a look at this curve here, so this density curve, this is a normal distribution. And normal distributions happen over and over and over and over and over again in our universe, and we're going to see exactly why that occurs today. But a couple of things about a normal distribution. First off, one more time, the area under a normal distribution is equal to 1 or 100%. So the distance between, or the area between the horizontal axis and the curve, you color all that in, that is 100%. In a normal distribution, the extreme values have very low frequencies. So you can see here that if you are taking a look at males that are over 6'4", it's probably more like around 6'5", there is not a lot of males walking around who are 6'5" or taller. And that is why that part of the line is so low. Because that part of the line, the higher it is, the higher the frequency is. And there are just not a lot of guys walking around that are 6'5". So intuitively, we can kind of see that this already is representing our reality. It's a nice representation of the different heights in our world. So we have the one extreme, 6'5" or higher, that has a very small frequency. We also have the other extreme on the other side of a normal distribution, also has a low frequency. So this would be individuals, males that are around 5'3" inches. And again, not a lot of males walking around that are 5'3". They're very infrequent, and that is represented again in this normal curve. And then the highest frequency of the normal curve is right there, and that is the mean of the normal curve. That is also the median of the normal curve. And in that case, this is the average height of 5'10". So in our world, the average height of males is 5'10", and by far, that is the highest frequency of heights for males. And then as you go further and further away from that mean, the frequency with which those heights are represented in our world, they get lower and lower and lower and lower until you get to really extreme heights, which are very, very rare. And again, that's represented by the curve of this normal distribution. All right, so those are the male heights. And you'll notice that the male heights have this very characteristic bell-shaped curve that the normal distribution has. And the female heights, right there, have the same shaped curve as well. So the heights of females, it is again a density curve. All of the frequencies are on or above the horizontal axis. The area under this density curve is equal to 1. And once again, you can see that the extreme values have a low frequency. So for example, women with a height of approximately 6 feet are a rarity in our world. So not a lot of females walking around that are 6 foot tall or higher. And then on the other end, also women who are shorter than 4'9" approximately are also very rare. So once again, you can see that the normal distribution represents the idea that very extreme values are rare in our society and our world in terms of heights. And then the mean height for females in our world is 5'5", and that is the most frequent height that is recorded. So the most frequent height is women who are 5'5", and then importantly, very close around that value is where you find the most individuals in this world, and that again is represented by the area under that particular part of the curve. So I mentioned that the density curve has an area of exactly 1 underneath it. And you might be taking a look at these two curves here, and you might be thinking to yourself, well, wait a second. If both of those curves have an area of 1, then how come they're different sizes? And doesn't that mean that they're different areas? And that's actually a really good observation, because if you take a look at the frequency of the average female height, that has a higher frequency than the frequency of the average male height. So there are more women who are 5'5" which is the average female height. There are more women who are 5'5" than there are males who are the average male height of 5'10". However, what this means necessarily is that if there's more frequency at the mean of your curve, then your curve is going to be more squished together, because that area has to be equal to 1. So if we take a look at the standard deviations of this curve, so this is the mean right here, and then this dotted line here is 1 standard deviation below the mean, and this dotted line here is 1 standard deviation above the mean for the female curve. If we take a look at the spread between 1 standard deviation above and 1 standard deviation below, just to kind of give us a graphic image of how spread out this curve is, we can then compare it to the male height curve here. And we have this dotted line here, which is 1 standard deviation above the male mean in height. So this is 1 standard deviation above. And then we have this purple line right here, which is 1 standard deviation below. And if we take a look at how far apart those two are, and then we just compare those two arrows, you'll see that the male curve for male heights is more spread out. It's wider. It has more variability. It has a greater range. So what this is telling you is that the reason that there are fewer males that are of average height is because male heights tend to be more spread out. So they have a shorter density curve, but it's a wider density curve. So the area equals 1. Women, on the other hand, have a taller density curve, but it's a narrower density curve. So again, the area is equal to 1. All right, so that is the intro to the density curves and what they are and how they look. Any questions about that? Okay, so one thing that I mentioned before is that it's very, very important that the density curve, in this case, has an area of exactly 1 underneath it. That's one of the things that makes this so powerful. But another thing that makes this particular curve so powerful is that it occurs over and over and over and over again in our universe. And it occurs so often that it is known as the normal distribution. And I meant to look up exactly why it's called the normal distribution, but I almost feel like it's called that because this is the norm. This is the normative distribution. This is just the distribution that happens over and over and over again. And if you measure populations on different continuous random variables, this distribution will come up again and again and again and again and again and again. So what statisticians and mathematicians have done is they have learned everything they possibly could about this normal distribution. So the normal distribution can be specified by 2 numbers. They can be specified by the mean of the distribution and the standard deviation. And once you know the mean of the distribution and the standard deviation, then you know everything you need to know about a normal distribution. So for example, for the male heights, the mean height for the male distribution is 5'10". The standard deviation is 7.2, or let me put that in centimeter, in inches. The standard deviation is 3 inches. So if somebody told me The average male height is 5'10", standard deviation is 3 inches. I could then create this entire curve and know everything about the curve just by those two numbers. So if you're dealing with a normal distribution, all you need is the mean and all you need is the standard deviation, and you will know everything that you need to know or could possibly know about this curve. So the normal distribution, we're going to be using it. We're going to be using it a lot, especially in the weeks to come. The formula for the normal distribution, the formula for the y values for a normal distribution is this formula right here. And what we're going to be doing in the coming weeks is we are going to be completely ignoring that formula because it's great if you're a mathematician, but it's not necessary for statistics. So I just wanted to put this up here just because I find it interesting that, it is that complicated and just that intricate. But what we're going to see is that to do statistics, people have already figured out everything that you need to know about that formula. So we're not going to have to use that formula. So thank goodness. But basically, you can see that for any value of x, if you want to know any height of frequency on this normal distribution, the only terms in there that you need to know are your standard deviation, right there, and the mean of your distribution. Everything else is known mathematical formulas, but that's enough of that. I think the point is made. You will see just how easy it is to use a normal distribution once we kind of get into it, but we're going to get into it next time. What we're going to do now, first, any questions on anything that we've covered besides the formula? Okay. All right, so what we're going to do now is we're going to build our own normal distribution. And the normal distribution that we're going to build is the distribution of IQ scores. So IQ scores are one of the most famous normal distributions. And it's usually, if you ask somebody what is meant by a bell curve, oftentimes they will mention IQ scores as what is represented by a bell curve. So IQ scores have that normal distribution. We have a mean, they are scaled to have a mean of 100 and a standard deviation of 15. And the higher you go in IQ, the less frequent individuals with that IQ occur in the population. The lower you go in IQ, the less frequent individuals with those IQs occur in the population. But it does have this normal distribution. It's one of the most famous of the normal distributions. So one of the things about IQ scores and intelligence just in general is that they've been very heavily studied. It's a topic of immense interest to a lot of people, even outside of psychology. And one of the things that they have discovered is that there are a number of different factors that contribute to an IQ score. So I'm going to list 10 of these, and we're going to be using 10 in this demonstration. So let's go through each of them very, very briefly in turn. So what are 10 factors, or the 10 most important factors in terms of contributing to an IQ, in terms of increasing your IQ or decreasing your IQ? So the first one that we have is genetic variation. So there are genetic influences on IQ. IQ is very heritable. So there are multiple genetics that can contribute to an IQ. And some genetic variation is going to contribute to a higher IQ. And importantly, some genetic variation is going to contribute to a lower IQ. So we got some genes that increase your IQ and some genetic variations that decrease your IQ. So that's one factor that contributes to your final IQ score. Factor number 2, we have your prenatal environment. So for your own IQ, how was your mother's health during the prenatal period? What was their access to nutrition? How high was their stress and their stress hormone levels? What kind of toxin exposure did they have during the pregnancy? So all of these things contribute either positively or negatively to IQ. So toxin exposure, negative contribution to IQ. Excellent maternal health and nutrition, positive contribution to child IQ. All right, next factor, we got birth outcomes. So things like preterm birth and low birth weights, they are linked to lower IQ scores later on in life. So what was the birth outcome? Was a person born under very excellent birth conditions, healthy weight, easy delivery, or at the very least, a healthy delivery, or were there complications? Did it come preterm? All of these things contribute to your IQ scores. All right, continuing on, early life nutrition. So did you as a child get adequate iodine, adequate iron, and overall diet quality? So this all contributes to proper brain development, and that in turn contributes to high IQ. So some people had wonderful early life nutrition, and because of that, their IQ scores go up. Other individuals had very poor early life nutrition, and because of that, their IQ scores tend to go down. All right, language exposure and stimulation. So if you have caregivers that talk to you often, that read to you often, that give you rich talk that is just slightly above where your current verbal levels and language skills are, that engage in cognitively engaging play, that boosts your IQ. And if you are lacking those, if you're maybe neglected or not socialized with early on, that would decrease your IQ. All right, quality and quantity of schooling. So not surprisingly, this one probably is one of the more known ones. But the more schooling you have and the better schooling that you have, that actually raises your IQ scores. And these effects are often seen with extended instruction and effective teachers. So basically, the more school you get and the better quality of schooling you get, the higher your IQ is. So the opportunities that you have for schooling all contributed to your final IQ score. Socioeconomic status. So this one, you kind of wish it was a little bit more equitable, but this is a factor in IQ scores. Parental education, parental income, and your neighborhood resources shape your access to learning and health supports, and that actually shapes or increases your IQ. So the higher your socioeconomic status, typically the better your parental education, the better their income, the better your neighborhood resources, the better the libraries you can go to, the better the schools you can get into, the more tutors you can hire. All of these things contribute to higher IQ. Lower socioeconomic status contributes to lower IQs. All right, we got three more. Health and disease burden. So things like chronic illness, uncorrected hearing and vision problems, parasite infections. These can all depress cognitive performance. So as a child, is the child healthy? Did the child avoid major illnesses? If they had communication problems because of hearing and vision problems, were those diagnosed early? Did they get glasses when they needed them in school? The more that these health and diseases are minimized, the greater your the more your IQ will increase later on. Last two, environmental toxins. So did you grow up in a place that had lead pollution, mercury pollution, and other air pollution? These all contribute to lower cognitive scores. If you lived in a very clean environment with very little air pollution, then you would have higher, or it would be associated with higher cognitive scores. And then finally, we have stress, adversity, and safety. So as you were developing, or just even now in your life, are you subject to chronic stress? Did you suffer from any of the adverse childhood experiences or ACEs, such as physical abuse, emotional abuse, physical neglect, emotional neglect? Was your mother treated violently? That's one of the factors. Kind of wish it was more equitable in terms of parent treated violently, but the role of the mother is still very emphasized in our society. Was there household substance abuse? Was there household mental illness? Was there depression or suicide attempts? Was there parental separation or divorce? Was there an incarcerated household member? if you suffered any of those effects as a child, that can impair your IQ scores. That can impair your cognitive development. And the opposite of that, a very stable, safe environment, supports development. So typically, it's very important to realize that these 10 things, these are just the 10 most important things that contribute to IQ scores and the development of intelligence. There's more things that also contribute, but this is one of the things that is very important to realize, especially if you are trying to improve the ability of individuals and you are trying to increase, for example, the intelligence of our society. Oftentimes when people think about IQ, they think about two factors. They think about genetic variation in the sense that, you know, my genes make me a genius and therefore my IQ is high. And they think of the quantity and quality of schooling, specifically that they went to a school and they worked hard and that's why their IQ is so high. But it's important to remember that all of these factors contribute to higher and lower IQs. So if you were interested in doing interventions in terms of increasing the IQ of our society, quality and quantity of schooling is only one factor. And you could provide better early life nutrition, prenatal care, and prenatal environments, reduce stress and increase safety, and that would also help to increase those IQ scores. All right, so those are the 10 biggest contributors to IQ, and I introduced those so that we have some context now for our follow along, do it with me demo. So what we're going to do right now is we're going to do a follow along, do it with me demo that's going to illustrate what a normal distribution is by helping us build our own normal distribution. So if you haven't already, you're going to want to open up the normal distribution IQ scores demo Excel sheet, and that is that Excel sheet right there. And we are going to just zoom in a little bit on this. We don't need to see the whole thing. Just while we're working on it at the beginning so that we can see exactly what's going on. All right, so while people are maybe still opening that Excel sheet, I'll just kind of break down what we're going to be doing here. So this is going to be our simulation of IQ scores. It's going to be us building a normal distribution. And what we have here is we have the contributing factors, and each contributing factor gets its own column. So here we have the contributing factor of genetic variation, prenatal environment, birth outcomes, early life nutrition, language exposure and cognitive stimulation, quantity and quality of schooling, socioeconomic status, health and disease burden, environmental toxins, and then stress, adversity, and safety. And then we have a column here that is going to give us totals for all of those. And then we have a column here that will calculate out the IQ scores. Now, I'm not going to say too much about how this calculation is exactly done, but what it does is going to take our total score here, and it's going to scale it to simulate an IQ score. So the two things that we know about IQ scores are that IQ score, the mean IQ for a population is 100, and the standard deviation is 15. And that's because the people that develop IQ tests develop them so that the mean for an IQ test is 100 and the standard deviation is 15. That's just how they're scored. All right, so let's start our simulation here. So what are we going to do to simulate this? Well, what we're going to do is for each of these factors, we're going to create an individual in the population. And we are going to randomly assign them either a high score or a low score on each of these factors. So the way that we're going to do that is we're going to start off with individual number 1 here. So individual number 1 is going to get row number 5. That's where we're starting off. So in column A, row number 5, right under genetic variation, we're going to tell Excel, we're going to give it a function. And the function that we're going to use is called rand. And what rand is, it is a function that returns a random number somewhere between 0 and 1. So to use this, we type in equals rand, R-A-N-D, and then we open parentheses, and then we just close the parentheses. There are no arguments that we need to give to random or to the rand function. The rand function just operates on its own, and then we hit enter, and then we hit got it. And we can see here that rand has given us a random number of 0.68. So it has generated a random number between 0 and 1. And one of the tools about, or things that you can do with rand is that if you go to an empty cell, so any of these empty cells will do, and you just hit delete, rand will recalculate itself. So the rand function now says, well, hey, I'll give you another number between 0 and 1. How about 0.5? And you can hit delete again, and it'll give you another number. Now it's 0.03. And you can hit delete again, it'll give you another number, now 0.5. And you can just keep doing that, and the rand function will just continually generate numbers that are somewhere between 0 and 1. So what does this number here mean in our simulation? What this number is this individual's score on genetic variation. So you can think of it in terms of the higher the score, the better their genetics are for IQ. So the higher the score, the more their genetics contribute to a high IQ. The lower their score, the more their genetics contribute to a low IQ. So here we have a score of 0.54. That is contributing an average amount to an IQ increase. If we have something like 0.85, this is somebody who has won the genetic lottery and has a very high genetic score. So they just by chance got a whole bunch of genes together that contributed to a very high IQ score. So that's reflected in that 0.85. Let's see if we can get something. Oh, 0.96. That's the super lottery. Okay, 0.07. This is somebody who has scored incredibly low on genetics. So this is somebody where whatever the genetic factors are that contribute to intelligence, they did not luck out on any of them. So any of the genetics that contribute to IQ, they went the opposite way. So they have a genetic variation that is going to contribute to a low IQ, an extremely low IQ in this case. All right, so this is one individual, and this is one factor. And what we're going to do here is we are going to now fill this, or fill a column, to simulate 1,000 individuals in our simulation, right? Oh no, we're doing more. We're going 10,000. I thought I was going to do just 1,000. No, we're going to do 10,000 here. So what we're going to do, so that we're not copying and pasting this 10,000 times, is we're going to use that tool that we saw before, where we can go up here to the name box. So we're going to go up here to the name box, and we're going to click on where it says A5, and then we're going to click again, and we're going to put in the colon, and the colon is going to tell Excel that we are giving it a range. And then we're going to pick a number so that we can get 10,000 scores. So the number that is going to give us 10, or the ending number that's going to give us 10,000 scores, is A10004. So we are basically telling Excel now, I want you to highlight all the way from A5 down to A10,004. That's going to give us 10,000 scores because the A5 is score number 1. So A10,004 will be score 10,000. It's always one less than what the difference is. So again, we have A5 colon all the way to A10,004. We hit enter, and that highlights 10,000 cells in that column A. And then what we're going to do is we are just going to use Control D for control down, and that's going to fill this random function for those 10,000 scores. So we go Control D, and now we have this random function for 10,000 separate individuals. So I'll just go all the way down there. You can see 10,000. And oh my gosh, what we have here is we have random scores for each of these individuals. And I said, oh my gosh, because we have somebody here, individual 9,994, maxed out, got the best genetics you can possibly get in order to contribute to a really high IQ. Individual 10,004 there, got 0.23. So not a very high contribution to their IQ, not a very high genetic contribution to their IQ. And again, you can see that there is a random variation here in terms of the IQ scores, the genetic variation scores for each of these individuals. So what does this mean? Well, what we're going to do here is we're going to see what happens when you only have one random factor determining your distribution scores. Because what we do here is we're going to go over to where it says total. And what this column here does is it simply adds up all of your contributions from genetic variation, prenatal environment, birth outcomes, etc. It adds all of them up into one grand total. Now, at this point, we're just adding one thing. We're just adding genetic variation. That's the only factor we've had so far. And then the next column over basically scales this number here so that it becomes an IQ score. So these numbers here have been scaled so that they have a mean of 100 and they have a standard deviation of 15. That's what makes them an IQ score. So far, so good? All right. And now we're going to take a look at the density curve. So on this sheet here, on the density curve sheet, you can click on that. And we have a density curve here that is way too big. 1 second, we zoomed in a little bit too much. There we go. All right, so now we have a density curve here. And we have IQ score here on the x-axis. And you can see that right here, right down the middle, is that IQ score of 100. That is the mean IQ score. And going to the left, we have lower IQ scores. And going to the right, we have higher IQ scores. And then we have the frequency with which these IQ scores occur across the 10,000 individuals here on the y-axis. And as you can see, this is a pretty flat density curve. This does not look like a normal curve whatsoever. And we can run a few simulations of this by just, again, choosing an empty cell and then hit delete. And Excel will recalculate the random numbers and it'll redraw the distribution density curve. And we can continue to do that. And you'll notice that for all intents and purposes, this is just a flat curve. So this is a flat curve because the high IQ scores, such as 123 or 125, seem to be just as frequent as the average IQ scores of 100, which are just as frequent as the low IQ scores over here of 75. So this is what happens when one single random variable is distributed through or contributes to a measure. So we have only simulated genetic variation. And we simulated genetic variation to just be a random number between 0 and 1. And that is reflected in the sense that this is an even distribution. This is a flat distribution. Now, some of you might notice that this bar over here tends to get very short sometimes. That's just an artifact of how Excel is graphing this because these are the leftover scores. So it basically tries to scale this so that we have the same number of bins, but this is the score this is the bin where we get the leftovers that are high but don't have as many. So it's just an artifact, don't worry about it. But the important thing is that we only have one factor here. And that means that we're going to have this flat curve. It's not a normal distribution. So how do we get to a normal distribution? Well, let's see what happens when we now add prenatal environment. So what we're going to do to add this is we're basically going to copy and paste all of these scores into the prenatal environment. So we're going to add another simulation here where we say, all right, we've taken a look at all the random variation, or we've simulated random variation in genetics, in the genetics. Now let's simulate random variation in prenatal environment. So we're also going to do the same thing where we're going to use the rand function. But thankfully, we have the rand function already done 10,000 times. So we can just go to that first score of genetic variation, and then we go shift control down arrow to highlight all 10,000 scores. And then we do control C to copy those. And if you need to allow it, please do. But we do control C to copy those. And then we just move over one column and we use control V. And it has now copied and pasted a new set of random numbers for prenatal environment. So let's take a look at what happened with this very first individual here. I'll zoom back in on this. So this very first individual here hit the genetic lottery, right? 0.98. You can only score as high as 1. So they hit the genetic lottery. They got a 0.98 on genetics. However, they lost out massively on prenatal environment. They basically had the worst possible prenatal environment. So on the one hand, this individual genetically, really, really high IQ. On the other hand, prenatal environment, really, really low IQ. So those factors are going to fight against each other, and this individual is going to end up with an IQ somewhere more in the middle. And then once again, if we just continually hit delete, it will recalculate these random variables. But importantly now, we have two factors. We have two factors that are contributing to IQ. So if we go over here, now our total is being totaled for two factors, and our IQ scores are still being scaled. So now when we take a look at our density curve, we'll zoom out of this just a little bit so we can see it again. Now when we take a look at our density curve, look what happened. It's not flat anymore, right? It is now, it's not bell curved, it's not a normal distribution yet, but it's getting there. It's not flat anymore because now we have two factors that are contributing to the IQ scores. And it's very rare that you're going to end up with two factors that are both really, really high. And that's why we don't have a high frequency of individuals with these high IQ scores. And it's very rare that we're going to get two factors that are really, really low. Both of them very, very low. And that's why we have a low frequency of very low IQs. Mostly, we're going to luck out on one and maybe get unlucky on the other, or we'll get kind of lucky on one and kind of lucky on the other and end up with a higher IQ, or maybe a little bit unlucky on one and a little bit unlucky on another and end up with a slightly lower IQ. But the point is that those extreme values now are becoming less frequent. And you can see that as we hit delete to just run this simulation over and over and over again, we just see more and more that this shape is basically going to stay stable, but not quite a normal distribution yet. All right, we're going to do this piece by piece just one more time, and then we'll fill in the whole thing. So once again, now we're going to add birth outcomes. So we have genetic variation, we have prenatal environment, we're going to add birth outcomes. Now we could copy and paste the formula that we have for prenatal environment and then, do the thing, control shift, arrow down to highlight the whole thing, copy, control C, paste, control V. However, we've already pasted or copied from the genetic variation, which has the exact formulas that we want. And you can see on this Excel sheet here that we do have this animated green dotted line. As long as you have that animated green dotted line, it means that whatever you copied is being outlined by that green dotted line. That is still active. That is still in the copy and paste memory of Excel. So we have already copied it. That's what this animated green line is telling us. So we can just go over here to birth outcomes. We can do control V and it'll paste those functions. So now we've added birth outcomes. So here on person number one, genetic variation, did not score very highly, has genetics that contribute to a low IQ. Prenatal environment kind of scored right in the middle. Not a great prenatal environment, not a bad prenatal environment, just kind of typical prenatal environment. But birth outcomes, amazing, right? 0.87, very close to 0.1. Birth outcomes were wonderful, good birth weight, healthy delivery situation. So the birth outcomes were great. Once again, now these three factors are being totaled in this column here and then scaled to form our IQ score. And then we take a look at our density curve. This time we're going to zoom out first. Take a look at our density curve. And now you can see that our density curve is looking even more like a bell curve. It's got even more of these scores are in the center area of the curve. Even fewer of the scores are getting very, very high or very, very low. So we're getting more of this bell-shaped curve here. And again, you can just choose an empty cell, hit delete, and you'll run this simulation over and over and over again. And you can see that with very small variations, the overall shape of this is not changing. This is getting closer to a normal distribution. All right, so let's finish this off. We did genetic variation. We did prenatal environment. We did birth outcomes. Now we're going to add in the rest. So we still have the genetic variation copied. It's still good to go. That green outline is still circling our formulas. So we can go over to early life nutrition, hit Control V to paste it, and took a little bit, but now we've simulated early life nutrition. Was it really, really good, contributing to high IQ? Was it poor, contributing to low IQ? We can go to language exposure and cognitive stimulation, Control V. Now we added that factor to the contributors to IQ. We can go to quality and quantity of schooling, hit Control V. Did you go to an excellent school and get a lot of it? Did you go to very poor schools and not get a lot of it? Now we simulated that. Socioeconomic status. High score means high socioeconomic status. Low score means low socioeconomic status. Health, disease, and burden. In this case, high score means very low disease burden, very good health. Low score means very high disease burden, very poor health. Environmental toxins, same idea. Low score means high levels of toxins. High score means low levels of toxins. And then finally, stress, adversity, and safety. And again, high score means very low stress, low adversity, high safety. Low scores means high stress, high adversity, very low safety. So now we have all 10 factors. And all of these 10 factors are contributing to this total here. That total is getting scaled in terms of the IQ scores. And now when we go to our density curve, we can see that it is very, very much like a normal curve. So this is with only 10,000 individuals. If we had 100,000, if we had 1,000,000, the computer might explode, but basically we would get a very, very much more smoothed out line. And if you just keep hitting delete, you will notice that this curve does not change its shape, that it stays that normal curve throughout all of the simulations. And we had that one really nice one that I wanted to end on. And maybe can we do, all right, we'll end it on this one. So you can see that, again, you can run this simulation over and over and over and over again. And you will end up with individuals here that max out on every single factor. Great genetics, great prenatal environment, low stress, great schooling, great caretakers. But there's very few that hit 0.9 or above on every single one of those factors. And that's why there are so few people with very, very high IQs. There's also very, very few people with extremely low IQs because, again, it's very rare that every single factor goes wrong and contributes to low IQs. But for most of us, we're going to be right here in the middle around an IQ of 100 or very close within one standard deviation of that IQ of 100. And that is because IQ scores are made up of very many different independent factors that all contribute to either a higher or lower IQ. And if you get high scores on a lot of these, you'll end up with a high IQ. And if you score low scores on a lot of these, you'll end up with a low IQ. And most people score high on some, low on others, in the middle on others, and end up with an average IQ. And that's why we get these normal distributions. All right, any questions on that, on building your normal distribution? All right. So what we're going to do now is just quickly just kind of put a pin in this and wrap this up. And I do want to point out one very important resource that you can try out before we meet next time. So hopefully this is giving you a little bit of insight into what a normal distribution actually is and why it exists. And one sort of public service announcement to just kind of go forward from this course or from this class with is that anytime you see a normal distribution for anything, so if you see it for IQ scores, if you see it for levels of depression, if you see it for empathy levels, if you see it for ability to engage in social situations, anything that you see a normal distribution for, the first thing that you should think is that, oh, okay, there's a normal distribution. Whatever the measure is, it's got a bunch of different factors. And too often, people will take a look at something like an IQ distribution and they'll say, oh, well, that's all just genetics. Or it's all just, whether or not you try in school, right? That's what IQ comes from. And the people that are geniuses, they're just born to be geniuses and they just tried really hard. And that is not the case at all. All of those factors contribute. So whenever you see a normal distribution, if anybody ever tries to tell you, oh, well, IQ is just a factor of this one thing, if there's a normal distribution, you know that cannot be true because it would not have that curve if there was only one factor contributing to it. All right, and then the last thing I'm going to mention is this website, www.stafflet.com/normal.html. This is what we're going to be using so that we don't have to use that horrible normal function, and also so we don't have to use Excel. So Excel can do a lot of the normal function calculations that we're going to need to do moving forward, but Excel can get a little tricky, and we do have this resource. So just really quickly, I'll show you what this resource is. So this is what it looks like. And what you can do is you can choose whether you want to calculate the area under a curve or if you want to calculate a value corresponding to an area. So let's take a look at the area under the curve and let's do the IQ. So we got a mean of 100, we got a standard deviation of 15. You can plot this distribution and it will immediately plot the normal distribution for this mean and this standard deviation. And remember I said those are the only two numbers that you need to completely determine a normal distribution. So you can choose any mean, you can choose any standard deviation, and then it'll plot the distribution for you. And then amazingly, it'll then allow you to calculate the area, if you chose calculate the area, between two values, to the left of a value, to the right of a value, outside of a region. So just to give you an example here, let's say that you wanted to know, let's say that you were doing a study on geniuses and you wanted to know out of the population, how many individuals are going to have an IQ score of 130 or more? Well, you can say, well, let me see, calculate the area to the right of a value. So let's put that value at 130. And then we go down here and we say, calculate the area. And it will draw in the area that you asked it to calculate. So you can take a look at this distribution and you can say, oh yeah, if this is the entire population, then this little blue area, that's everybody with an IQ of 130 or more. And then it calculates the area and tells you, well, you're looking at about 2.28% of your population. And what that basically means is that if you want to recruit 3 people for your study who are geniuses, you're going to have to talk to 100 people just to get 3. And you can do so many really cool things. So if you wanted to know, well, how many people are between 1 standard deviation above, which is 115, or 1 standard deviation below, which is 85, calculate the area. Very, very importantly, it draws the area in blue that it thinks you're asking it for. So immediately you can take a look at the distribution and say, oh yeah, that's the area that I meant. But if you did something like this, you'd be like, oh, wait a second, no, I don't want the outside area. I want that inside area. Boom, that's what I was looking for. And then it calculates that area for you right there. So we are going to be using this next time that we meet, when we are going to go through a bunch of different scenarios and kind of see how you can use the normal distribution to answer questions in psychology, to kind of determine policy, determine decisions that you make. So I would highly, highly recommend check this website out, play around with it a little bit, just goof around with it a bit, put in some numbers, try out some different things, get a little bit familiar with it, because next time that we meet, we're going to go through a bunch of scenarios. I'm going to try to pack in as many as we can in our meeting where we just try to answer things based on that normal distribution. All right, any questions on that before we wrap it up? All right, so that is all that I wanted to cover for today. So that was your intro to normal distributions. Next time, we are going to be calculating the area under a curve. We're going to be using area to calculate values. So we're going to put that into a psychological context so you can see how a psychologist would actually use this. But that's all going to be next time. As for today, we're done with what I wanted to cover.